second lecture, we will see the energy band diagram of semiconductor. The topics to be covered are silicon energy band diagram, the concept of forbidden band gap energy, the direct and indirect band gap semiconductors, and Fermi-Dirac probability density function. If you look at the semiconductors, we already seen that if you look at the free electron concentration, if the concentration is between 10 to the power of 6 and 10 to the power of 21, what you get is we get a semiconductor. So if the free electron concentration inside a material is somewhere between 10 to the power of 6 and 10 to the power of 21 centimeter raised to minus 3, then we get a semiconductor. So you can see that from 10 to the power of 6 to 10 to the power of 21, that means we can multiply this with the factor 10 to the power of 15. So we can have a large dynamic range. So this range, we can say that there is a large dynamic range. And because of this large dynamic range, the semiconductor find importance in electronics. So we already seen that the elemental semiconductors, if you look at elemental semiconductors, they are basically the G4 elements in the periodic table. The G4 elements, one is silicon and the other is germanium. The silicon has got an atomic number 14 and germanium has got an atomic number 32. Otherwise, we have compound semiconductors. Compound semiconductor, it can be like gallium arsenide, or it can be indium phosphide, aluminum phosphide, etc. But these are special purpose devices. If you look at the silicon atom model, silicon, it has got 14 electrons because it has got an atomic number 14. That 14 electrons occupy the different energy states like 1s2, 2s2, 2p6, 3s2, 3p2. That means we have a positive charged nucleus. This is the nucleus of the silicon atom, and this is the orbital number n equal to 1. This is orbital number n equal to 2. This orbital number n equal to 3, where n is a principal quantum number. In n equal to 1, we have 2 electrons. N equal to 2, we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And n equal to 3, we have 4 electrons. So this n equal to 3, we call it as the outer orbit, outermost orbit. This is the silicon atom model. Look at the bond model of silicon. The group of elements normally form a covalent bond. So the silicon atoms make use of covalent bonds. Covalent bonds is basically sharing of one electron with neighbor atom. The neighbor atom, which is normally considered as the strongest bond. It is the strongest bond. Remember that when you operate at T equals 0 Kelvin, that is minus 273 Kelvin, minus 273 degrees centigrade, sorry, minus 273 degrees centigrade, okay, not Kelvin, minus 273 degree Kelvin is degree centigrade. The silicon is basically insulator. Since there is no energy, no bonds will break, hence no free carriers. Therefore silicon is an insulator, because no free carriers available in silicon. But as temperature increases, what happens is bonds will break. There is a breaking of the bond, and the free carrier concentration increases. The free carrier concentration increases. Look at the hydrogen atom model. The hydrogen atom model, the first model is a Rutherford model. The Rutherford model of the atom. Hydrogen, it is having an atomic number 1. That means 1 electron. So we have a positive charged nucleus, the nucleus of the hydrogen atom, and the electron is orbiting around the nucleus at some orbital distance. So the electron is here, that one electron is orbiting at some orbital distance from the nucleus. That orbital radius is A0. So the quantity A0 we call it as the orbital radius, and you seen that this value is equal to 0.529 Armstrong unit. Remember, 1 Armstrong unit is 10 to the power of minus 8 centimeter, otherwise 10 to the power of minus 10 meter. So the orbital radius of the electron is A0, which is given by 0.529 Armstrong unit for hydrogen atom. We have the Bohr model. The second model is the Bohr model of the hydrogen atom. So we can say that we have a positive charged nucleus. This is a positive charged nucleus, and the electron is orbiting around the nucleus. But where is electron orbit? It forms an electron cloud around the nucleus. Electron cloud. The failure of the Rutherford model is what is seen in hydrogen atom. When the hydrogen atom electron is excited to higher energy levels and later it is cooled down, it is seen that the hydrogen atom emits discrete line spectrum. That means it emits lights having discrete wavelength, not continuous wavelength. Why the hydrogen atom can emit discrete wavelengths cannot be explained by using the Rutherford model, whereas the Bohr model helps in explaining the emission of light. So we have the positive charged nucleus, and the electrons can occupy discrete energy states like this. This is n equal to 1, which is a ground state, then n equal to 3, 2, 3, etc. So n equal to 1 we call it as a ground state. So the electron is residing at this particular state. When you give energy to the electron, what happens is this electron will make a transition from n equal to 1 to n equal to 2, and if you give further energy, it again make a transition from n equal to 2 to n equal to 3. So these states n equal to 1, 2, 3, they have a discrete nature. They are the discrete energy states. It is seen that when you cool down that hydrogen atom, the electron that is there in the state E3, it can come down to state E1, can do a reverse transition, and during this reverse transition it loses energy equal to delta E, and this energy is released in the form of a photon. There is a photon emission, light emission. It is seen that the quantity delta E equal to E3 minus E2, we can write this as equal to Hf, where H is a Planck's constant and F is a frequency. So this can also be written as frequency is c by lambda. Therefore, the wavelength of the light emitted will be equal to Hc divided by delta E. So this is the wavelength of the light that is being emitted by the hydrogen atom when the electron make a transition from the state 3 to state 2, that is from n equal to 3 to n equal to 2. The hydrogen atom emission spectrum is as shown. So this spectrum is a discrete spectrum. Discrete means line, is a line spectrum, and the wavelength of the light emitted is given by Hc divided by delta E, where H is the Planck's constant. Which is given by 6.626 multiplied by 10 to the power of minus 31 joule second. This is a hydrogen atom emission spectrum. So if you look at the energy band diagram of the hydrogen atom, so you can see that at lower temperature the electron will be here, that is for temperature T1. Then for temperature T2 greater than T1, it can go to the second state, and temperature T3 greater than temperature T2, you can go to state 3, and these electrons will form, this electron will form a cloud over the nucleus. So what is the energy of the electron in a given state is given by minus of m0 e raised to 4 divided by 8 h square epsilon 0 square n square, that much joules. This is the energy of the electron in a given state, where m0 is the rest mass of the electron, E is electron charge, H is a Planck's constant, epsilon 0 is a permittivity, absolute permittivity. Remember that for hydrogen atom, the relative permittivity epsilon are equal to 1. By substituting this, what is the energy of the electron in the nth orbit is given by minus of 13.6 divided by n square, that much electron volt. This is the energy of the electron. So based on that, we can draw the energy band diagram for hydrogen. Assume that this is the energy E in electron volt. Okay, the lowest energy state, remember that the energy of the electron in the end state En is given by minus of 13.6 divided by n square electron volt. So n equal to 1, the electron will be in the ground state. This is n equal to 1, having an energy minus of 13.6 electron volt. When it jumps to, this is n equal to 2, when you put n equal to 2, we get minus 3.4 electron volt. Put n equal to 3, this is n equal to 3, you get minus 1.5 electron volt. This is n equal to 4, you get an answer. Similarly, goes like that and finally reaches 0. This 0 electron volt. So when an electron is in this excited state, when it falls through this gap, it loses energy equal to delta E, and delta E is given by h c by lambda. So what happens is, there is a photon emission that is taking place. So this is the energy band diagram of the hydrogen atom. So n is equal to 1, we call it as the ground state. And these states are all excited states. Look at an isolated silicon atom. What is isolated? Okay, isolated silicon atom means it is non-interacting. There is only one silicon atom. One silicon atom, we have 14 electrons are there. The 14 electrons are arranged like this: 1s2, 2s2, 2p6, 3s2, 3p2. Okay, so if we just look at the band diagram, we have 1s, this is 2s, 2p, 3s and 3p. starting from the ground state. This is 1s, 2s, 2p, 3s, 3p. 1s has got two states. Remember that the two states are discrete states, but the states are separated by a very small gap, normally of the order of around 10 to the power of minus 19 electron volt. So we represent the two states by using a single line. The two states are merged together to form a single line, and 1s can have 2 electrons. Similarly 2s, 2 electron. 2p, we have 6 electrons are there. And 3s, 2 states. And 3p, we have 6 states are available. In that 2 states are occupied, and remaining 4 states are empty. So remember, cross indicates filled state, and circle indicates empty states. And this is the energy. It is going higher up, E in electron volt. So the 14 electrons are distributed throughout energy states like this. So if you look at the outermost orbit, that is 3p, you can see that 2 states are filled and 4 states are vacant. Vacant 4 states are there, that is empty. Now take n isolated silicon atom. Again we have n non-interacting silicon atoms. The spacing is the space far apart. Okay, there is a distance, so the spacing is very large. Spacing large. So because of spacing very large, no atomic interaction. No atomic interaction. So how many electrons are there? So we have 14 n electrons are available. This much electrons are available. So how will you distribute this? So like the previous case, we have start with 1s, 2s, 2p, 3s, 3p. So in 1s we have 2 states, so there will be 2 n electrons are available. 2s, 2 states, therefore there will be 2 n electrons available. 6 states, so we have 6 n electrons available, 2 n electrons available. This is, so you can see here we had 2 n filled and 4 n empty. Empty states are available. This is a band diagram of n isolated silicon atoms. Remember that every state, for example 1s has got 2 states. The 2 states are separated by a small energy gap, but that energy gap is negligible. Therefore we represent by using one single line. So they merge together to, many states will merge together to form one single line. It is based on the fundamental principle that no two electrons can occupy the same energy state at the same instant of time. Now what happens when the spacing between the atom decreases? When spacing decreases, what happens is there will be atomic interaction. There is an atomic interaction. That means chemical bonding takes place. There is a chemical bonding takes place. That means normally in chemical bonding only the outermost shell electrons will take part in bonding. Outermost shell electrons will interact. This interaction leads to two phenomena. This leads to A. Covalent bonding, and B. We have another phenomena called as band bending. As the distance decreases, there will be a band bending is there. So what is that band bending? If you want to see, I just show like this. This is a energy in electron volt, and this is the atomic distance. Atomic distance. So we can have band bending, or we say band splitting. So when the distance is too large, we have 1s, 2s, 2p, 3s and 3p. 3p, 3s, 2p, 2s, 1s. So here we have n 2n electrons, here also 2n, here we have 6n, 2n, 2n filled and 4n unfilled. So here we have 2n, here we have 4n. 4n states unfilled. This is the case where the distance is too large. So here it is isolated atoms. As the atomic distance decreases, when the atoms were brought nearby, what happens is nothing happens to 1s, so nothing happens to 1s, nothing happens to 2s, nothing happens to 2p, but what happens is the 3p and 3s begins to split. Like that they can split into so many states. This phenomena is called as band splitting. That band splitting is due to the atomic interaction. So as the distance between the atom decreases, the electrons in the outermost orbit, they begin to interact, thereby leading to covalent bonding, and this phenomena is represented in the band diagram by using energy band splitting. So you can see that as the distance further decreases, so this is the atomic distance, as atomic distance decreases, when you move down like this, distance is decreasing, what happens, you can see that this is the splitting of 3p and 3s. This is splitting of the energy bands. Later what happens is, and remember this 3p has got 2n stage field, this also 2n stage field, 2n field, 2n field, and 4n empty. This is 4n empty state. So what happens is, this band splitting leads to, you can see that the bands will merge, forming 4n and 4n stage, total 8n. So 4n stage filled and 4n empty here. And when you take out this particular atomic distance somewhere here, if we just look at this distance, what happens is, at this atomic distance normally a metal crystallizes. At this distance we have a metal crystallizes. So you can see that the 4n stage filled and above that the 4n stage unfilled without any gap. As the distance further decreases, the bands further split, and at some distance here, and this some distance, the distance I name it as A0, what happens is a semiconductor crystallizes. So we can see here in the diagram, we have here 4n states filled and 4n states empty, separated by a forbidden gap. So this we call it as the forbidden gap. There are no permeate energy states. There are no states available in that particular region. And that forbidden gap energy difference, we name it as Eg. Okay. The value of A0, if you look at, A0 is a lattice constant for semiconductor. There is a lattice constant. For silicon, the value of A0 will be 5.43 Armstrong unit. So if we simplify the band diagram, so at this lattice constant, if we just look at the diagram and project it, can be shown like this. This is energy in electron volt. This level these points we can project it, and we mark this as EC and EV. What is that EC? EC we call it as a conduction band edge. And what is EV? We call it as a valence band edge, the edge of the valence band. So you can see that here all the states are filled. Okay, so we have 4n filled state, and this is 4n empty, and the difference between these two, we name it as the band gap energy Eg in electron volt. So the diagram can be simplified like this. So if we just look at the energy band diagram of silicon, so we have a silicon crystal. This is my silicon, having the dimension x equal to 0, x equal to L. Okay, and if you look at the semiconductor, now what are the number of atoms per centimeter cube for silicon is equal to 5 multiplied by 10 to the power of 22 per centimeter cube. So this many number of silicon atoms are available in 1 cubic volume. So when you look at the silicon atom, how will you draw that? First we want a reference. The reference is denoted by E0. What is E0? E0 is the free space or vacuum energy level. Vacuum energy level. If we know the free space energy level, we can draw where is a conduction band edges. This is EC. This is a bottom edge of the conduction band. Bottom edge of the conduction band. The difference between E0 and EC is defined as the electron affinity, denoted by E psi, which is equal to 4.05 electron volt for silicon. Okay, where what is this psi? Psi is called as electron affinity. It is a potential. So that E psi is given by E0 minus EC. And once you know the conduction band edge, we can draw where is a valence band. This is the valence band edge. So that is a top edge of the, it is the top edge of valence band. Difference between the conduction band and the valence band edge denoted by Eg. That is the band gap energy. So Eg is given by Ec minus of Ev. So this is the energy band diagram of silicon. We look at the band gap energy. So the quantity Eg we call it as the forbidden gap energy. By definition, what is Eg? Eg is given by the difference between Ec and Ev. That much electron volt. Okay, this Eg is also the covalent bond strength. Covalent bond strength. If we give an energy equal to Eg, then we can break the bond, thereby generating electron hole pairs. So bond strength equal to the band gap energy. This quantity Eg depends upon two parameters. One depends on material. It is material dependent, whether it is silicon, germanium, gallium arsenide, etc. And also depends on temperature. Depends on temperature. So Eg depends upon the material and also depends upon temperature. We want to look at the temperature dependence of Eg. What is seen is, as temperature increases, what about Eg? It is seen that Eg decreases. That means it has got negative temperature coefficient. It is seen that from literature, it is seen that Eg for a temperature T Kelvin is given by Eg for 0 Kelvin minus alpha times T square divided by T plus beta. Remember, T is a temperature in Kelvin, and look at alpha beta. They are basically fitting parameters, curve fitting parameters. So you can see that Eg at 0 Kelvin for germanium, silicon and gallium arsenide given here. Okay, the value of alpha is given by this value and the value of beta is given by this one. This is from literature. Okay, from literature. You can refer any standard book which gives you these values. They are obtained practically. Okay, so what is Eg of different semiconductors at different temperature you want to find out, you can make use of this equation. So this is an empirical equation. So what is the effect of temperature on Eg? So what is seen is temperature is increasing. What happens? Vibration of the lattice atoms will increase. Vibration of lattice atoms increases. So what happens is this leads to an increase in the atomic separation. Atomic separation increases. The distance between the atoms increases. When the atomic separation increases, the electrons will experience less periodic potential inside a silicon crystal. Periodic potential, the distance increases. So we can say that the nucleus has got a positive charge. In between we have zero potential. So we have a periodic potential in the silicon crystal, and because of that, what happens is the band gap Eg decreases. Therefore, we can say that Eg has got a negative temperature coefficient, NTC. Negative temperature coefficient. What is seen is for silicon, if you look at silicon, what is Eg for a temperature T Kelvin will be, the simple equation is Eg for 0 Kelvin minus 3.6 multiplied by 10 to the power of minus 4 multiplied by T Kelvin. That is for silicon. And for germanium, Eg for temperature T will be Eg for 0 Kelvin minus of 2.23 multiplied by 10 to the power of minus 4 multiplied by T Kelvin. These are two empirical equations for finding out Eg for any temperature. For 0 Kelvin, the value of Eg for silicon and 300 Kelvin value of Eg for silicon, germanium, gallium arsenide is as shown. We want to see the different types of semiconductors. One semiconductor is called direct band gap semiconductor and second is called the indirect band gap semiconductor. So what is a direct band gap semiconductor? In a direct band gap semiconductor, you can see that this is a conduction band, this is a valence band. When you plot the energy band diagram, that is a EK diagram, so So this is your energy E in electron volt, and this is K, the crystal momentum. You can see that this is the top edge of the top edge of the valence band denoted by EV, and this is the bottom edge of the conduction band denoted by EC. If the top edge of the valence band and the bottom edge of the conduction band, if they align for the same value of K, then we say that it is a direct band gap semiconductor. So this is direct band gap semiconductor. The top edge of the valence band and the bottom edge of the conduction band, they align for the same K. Okay, then we say direct band gap. So if you plot it, if they don't align for the same K, so you can see that the top edge of the valence band is here, the bottom edge of the conduction band is here. They don't align for the same value of K. So this is for K1 and this is for K2. Okay, then we say that is an indirect band gap semiconductor. So this is indirect band gap. Band gap semiconductor. A direct band gap semiconductor will allow the transition of electron from the conduction band to valence band directly, or from valence band to conduction band directly. So there is a direct transition possible, and in that transition what happens is the electron is moving from a conduction band to valence band, it emits light. So there is a photon emission possible. Photon emission. Therefore, direct band gap semiconductors are normally used in optical devices. An example of a direct band gap semiconductor is gallium arsenide, which is normally considered as a building block of optical devices, say LED, light emitting diode. Whereas an indirect band gap semiconductor will not allow the direct transition of the electron from the valence band to conduction band, or from conduction band to valence band. What happens is, whenever there is a transition takes place, there will be a phonon emission. Phonon emission. Phonon means it is an acoustic vibration of the lattice atom. This transition is enabled with the help of an impurity site or defects. Only if there is a defect or there is an external impurity that is present, at these sites the electron have a transition from valence band to conduction band, or conduction band to valence band. Example of indirect band gap semiconductor, they are silicon, germanium. These semiconductors cannot emit light. So silicon, germanium, they are not basic building block of light emitting diodes. Whereas gallium arsenide is normally used to fabricate LEDs, because it allows the direct transition from conduction band to valence band, thereby emitting a photon. So we study more about direct and indirect band gap semiconductor when you look at the topic of optical devices. So what are the different types of particles that is present in a semiconductor? One, we have electrons. Second, we have holes. Third, photons. Fourth, phonons. The electrons and holes together we call it a fermions. Fermions, they are normally studied by solving Schrödinger equation. The Schrödinger wave equation. By solving the Schrödinger wave equation, it is possible to characterize the motion of electrons and holes. The photons, the basic particle we call it as a boson. Okay. Normally we can characterize these photons. Photon is basically an electromagnetic wave. So we can use Maxwell's equation. Because it is an EM wave. Electromagnetic wave. Light is an EM wave. So by using the Maxwell's equation, it is possible to characterize photons. Whereas, look at phonons. Phonons are basically lattice vibration. The vibration of the lattice atom. It is an elastic acoustic wave. It is an acoustic wave. Like sound wave. The crystals will begin, the lattice atoms begins to vibrate, thereby creating a sound wave, an acoustic wave. That is what a phonon is. So these are different types of particles that you come across in semiconductor. You want to look at the wave particle duality. The wave particle duality says that matter or energy can propagate in the form of particle or wave through a medium. So that we call it as the duality principle. So associated with the particle, we have two parameters. One is energy E, which is given by hf, and second we call it as a momentum P, given by h by lambda. Okay, so E is the energy of the particle and P is the momentum of the particle. They are basically the characteristics of particle. Energy and momentum, they are the characteristics of particle. Whereas F is a frequency, lambda is a wavelength. They are basically the characteristics of a wave, a traveling wave. So you can see that energy and momentum, frequency and wavelength, they are connected through this equation, E equal to hf and P equal to h by lambda. So we know what is h is. H is a Planck's constant. H is equal to, what is that, 6.623 multiplied by 10 to the power of minus 34 joule second. So we want to find out the wavelength corresponding to 1 electron volt. So we have E equal to hc by lambda, that is hf. So what is lambda? That is hc by E. Substitute 6.623 10 to the power of minus 34 joule second multiplied by C, 3 into 10 to the power of 8 meter per second, divided by E, 1 electron volt. So remember, 1 electron volt equal to 1.6 multiplied by 10 to the power of minus 19 joule. So to substitute here, 1 electron volt is 1.6 multiplied by 10 to the power of minus 19 joule. So the value of lambda will come out to be 1.24 micrometer. Okay, so that is the value of lambda. Lambda corresponding to 1 electron volt. For any other E, for E not equal to 1 electron volt, what is lambda? We get lambda equal to 1.24 micrometer divided by E, you put it in electron volt. That is the value of lambda for any other energy. 1.24 micrometer. Normally, if you look at the electron hole behavior, you want to study about electron hole behavior, we invoke the probability. So we use probability density functions, PDF, probability density functions, to study about the behavior of electrons and holes. So we have electrons and holes, we call it as a fermions, satisfy a Fermi-Dirac distribution function, Fermi-Dirac probability density function, B Maxwell-Boltzmann probability density functions. So there are two probability density functions which can be used to characterize the behavior of electrons and holes. And if you look at the photons, we make use of another probability density function called as Bose-Einstein probability density function, used to characterize the behavior of photons. So what is the Fermi-Dirac probability density function? The probability density function is given by ft of E is 1 upon 1 plus e power E minus Ef by kT. So what is this quantity f of this one? This is basically f of E comma t. What does it do? It is a probability that a given energy state E is occupied by an electron, at a temperature T. That is what f of E comma t is. The quantity Ef, this is called as a Fermi energy level. Now at E equal to Ef, what is f of E comma t? Will be equal to 1 by 2. So it is an equally likely case. So what is f of E comma T? It is a probability that a given energy state E is occupied by an electron at a given temperature. So what is the probability of finding an electron at the Fermi level? It is given by f of E comma T will be equal to 1 by 2 from this equation. You want to understand what is a Fermi-Dirac distribution function. So we make use of an analogy. We call it as a beaker analogy. Beaker analogy. I consider T equal to 0 Kelvin. We have a beaker which is filled with water up to this height. The height is h. So here water is there, and here it is air. The height indicates potential energy, and this axis, if we take it as the probability, where this point is P equal to 0, this point is P equal to 1. So if the beaker is in equilibrium, at equilibrium, if you look at up to the height h, all the states are filled, and above the height h, all the states are empty. We can think that way. That means when you plot the probability density function, this is the height h, this is P equal to 0, P equal to 1, P equal to 1. Up to the height h, all the states are filled, and above the height h, all the states are empty. So what is the probability of finding electron above h? 0. So above h will be 0, and suddenly the probability switches to 1. So this is the plot of the probability density function at T equal to 0 Kelvin. So if we consider any height h, any height above h, there is no water, and any height below h, it is filled. So this is analogous to what is that? All the states below h is filled, and all the states above h is empty. And this height h corresponds to the Fermi level EF. So we can say that if we look at the Fermi energy E less than EF, E less than AF, they are the filled states. And if you look at E greater than EF, they are empty states. So where is EF? So you can say that EF lies above the topmost fill band. The topmost fill band. So if you disturb the equilibrium, what happens is disturb equilibrium. You disturb the equilibrium. So we have the beaker. Up to the height h filled with water. The height h corresponds to the Fermi level. this I take probability 0, this I take probability equal to 1, and I disturb the equilibrium by increasing the temperature of the beaker. When you increase the temperature of the beaker, what happens is this water level will change because the water molecules get heated up, they get agitated, and this, what happens is the surface will not be in equilibrium. So what happens is, as the temperature increases, higher states will be occupied, and as the temperature increases, higher states will be occupied. This is for a temperature T greater than 0 Kelvin. Okay, and this corresponds to 0.5 probability. Okay, so this plot we can call it as f of E comma T. As the temperature increases, higher states will be filled and lower states can be empty. That is what a Fermi-Dirac distribution function is. The Maxwell-Boltzmann probability density function is derived from Fermi-Dirac distribution function. So we have the Fermi-Dirac distribution function f of E comma T is given by 1 upon 1 plus e power, it is E minus of EF by kT, where k is a Boltzmann's constant. Okay, if E minus EF is greater than 3 kT, the quantity f of E comma T can be approximated to e power minus of E minus EF by kT. And if E minus EF is less than minus 3 kT, f of E comma T can be approximated to 1 minus of e power E minus of EF by kT. Okay, is based on the approximation that 1 divided by 1 minus of 1 plus x, 1 divided by 1 plus x is approximately 1 minus x. Okay, so these two functions we call it as a Maxwell-Boltzmann density function. So the graph, if this is EF and you have the probability density function going like this, this levels we take it, this difference is 3 kT, 3 kT above EF, or you can take 3 kT below EF. So here we can use Maxwell-Boltzmann approximation, Maxwell-Boltzmann PDF, and here also we can use Maxwell-Boltzmann PDF here also. Maxwell-Boltzmann PDF is applicable in that region. In between that we can use Fermi-Dirac distribution function. So what are things we have studied here? One, we have seen the band model of silicon first. Second, what is the band gap energy Eg? What is the temperature dependence of Eg? Eg as a function of temperature. How the band gap depends upon temperature. And third is the Fermi distribution function, the Fermi Dirac distribution function. F of e comma t, and then we use approximation. We call it as a Maxwell-Boltzmann approximation. That Maxwell-Boltzmann approximation is derived from the Fermi Dirac. Thank you.